I'm Aniket Borwanker, so I work as a development manager for composite strengthening systems with Simpson Strong Tie.
Welcome to the Structural Engineering Podcast. This week we're talking with Aniket Borwanker, a project manager at Simpson Strong Tie. Aniket's job at Simpson is to help them test and develop new products and uses for FRP. That's fiber reinforced polymer. Aniket did a master's at Vanderbilt where he researched FRP bonding. That's how he got his background in this. After school, he went out in the field to do traditional structural design for many years and then had the opportunity to join Simpson and help work on this cool product line. I've gotten to use FRP a few times and it still has this feel of a magic, ultra strong material to me. With Aniket, we learn it's not exactly magic, but there are a ton of uses and it's a great resource to understand for when you're in a tight spot or just working on a retrofit project. So please enjoy our conversation with Aniket. If you have any questions, Simpson is great about helping designers understand and use their products. I ask the field guys all sorts of ridiculous questions and they don't seem to mind that much. So feel free to reach out to them. Okay, so we talked very briefly before, and I kept using the word fiberglass, and you said, "Well, it's not really fiberglass, right? There's more to it." So, Can you tell us, like, what is FRP, and maybe like why is calling it fiberglass not quite correct?
So FRP is basically a combination of any kind of fibers and an epoxy. So typically, the most commonly used structural strengthening fibers are either carbon or glass. So FRP is a composite, so your fibers provide the tensile strength in the composite, and your epoxy makes that into a composite and as well as transfers forces from your fibers back to the substrate. Also, this is an externally used reinforcing, so your epoxy protects your fibers from any kind of damage. So that is FRP in general. Now, when you mean fiberglass, it's typically what it means is glass fiber reinforced composites, but then you also have carbon fibers, which is used quite a lot in structural strengthening type applications. So I generalize it as FRP, and then fiberglass is part of FRP.
Could you kind of tell us, a little bit about the type of fiberglass products or FRP products, let's say, that are out there for reinforcing specifically concrete?
Yeah. So the main for reinforcing concrete, we use a lot of carbon fiber-based composites. So this is either unidirectional or bidirectional carbon fibers saturated with an epoxy resin, which are externally applied on your concrete substrate. We use glass fibers too. Glass fibers are less strong than carbon fibers, so typically concrete needs more strengthening. You end up using more carbon versus glass. But if it's like a protection-based application, a lot of DOTs wrap their bridge columns with glass fiber so that it protects these columns from any corrosion or damage. Also, glass gives a lot of ductility. So when you're looking for just ductility and less strength, that's where glass fibers can be used quite a bit. Also, something similar is also FRCM. So it's a fabric reinforced cementitious matrix. It's also a composite where instead of just fibers and an epoxy, now you have a carbon fiber mesh and a cementitious matrix. So it's similar type of strengthening, but has different materials that you can use to strengthen concrete as well. So these are primary externally applied reinforcing composites that we use for strengthening concrete applications.
Across all these products, what is the sort of range of strength that we're looking at? Like a glass fiber, how strong is that? Is it compared to any material that we're sort of used to?
Yeah, so I mean, if you're looking at the composite properties of carbon versus glass, your carbon fibers typically is like about 128,000 KSI tensile strength versus glass is around 56,000. So, I mean, carbon is maybe twice as strong as glass would be. So those would be your typical range. Now you do have laminates, like again, they're pre-cured carbon fiber strips that are about 180 KSI. So they are a little stronger than field saturated carbon fiber fabrics. So this is your range between glass fiber versus carbon fiber. Mm-hmm. I mean, there's some research going on. They used aramid fibers before, but they don't use as much of aramid fibers right now. There's some research going on for basalt fibers, so that's another upcoming area of using basalt fibers for strengthening as well.
this might be kind of silly or I'm looking at it wrong, but when we're looking at fibers, really it is only a tensile capacity that any of these things have, right? Like any shear we're adding to a wall, we are just adding tension in the right plane.
This is purely a tensile reinforcement. You're correct.
Okay.
So that's what. So it's like externally applied steel where you're adding more tensile capacity to your member.
Mm-hmm.
How long has FRPs been around in the commercial realm? I understand they've probably been in research probably for maybe a little bit longer, but commercially, how long have they been available?
I would even go back to maybe early 90s that FRP started getting more commercialized. So I would say maybe 25 years plus, we have a good history of composites being used in construction or retrofit of structures. It's becoming more and more common now, like with ACI coming up with good design guides and your evaluating agencies, ICC and all coming up with good testing criteria. So it's becoming more mainstream for sure at this point.
Since you mentioned ACI, where does fiberglass, FRP, carbon, where does that all fall in as far as ACI sees it currently? Is there a section in our typical ACI 318 that references these products?
ACI has a design guide, which is 440.2, that is for strengthening of structures, concrete structures with externally applied FRP, and 440.7 is for masonry structures.
Mm-hmm.
So ACI 354 basically refers to FRP as an externally applied strengthening material, but it's still not part of building code. So I know CBC now has FRP as part of it that refers to FRP design guides. So it's becoming more and more mainstream, but the main guides that we use for design are ACI 440 for concrete and 440.7 for masonry.
Okay.
So I guess to kind of show or discuss the whole range, what are the different forms of FRP that you can kind of readily, get, knowing that there's different types of maybe weave patterns or strengths as well?
So the most readily available fabrics come in rolls. So these are typically rolls that are either 25-inch wide or 50-inch wide or 12-inch wide rolls that are basically dry fiber fabrics that you would saturate with an epoxy. These come in either unidirectional or bidirectional weaves. So unidirectional is basically adding strength in one direction, like what you would have your steel there. Bidirectional, again, you have multiple weaves in bidirectional. One is like a 45 degree. We use that a lot for shear transfer. So if you're transferring shear between your diaphragm to a concrete wall, that would be another 45 degree weave. Or if you're trying to transfer shear between double T's on a roof structure or a floor structure. So that's another area or another type of FRP weave. Also, we have pre-cured laminates. So your regular FRP is something that you saturate with an epoxy on the job site, whereas pre-cured laminates are something that are already saturated in the factory. So these come in rolls, pre-saturated carbon laminates, and then you just apply it with an epoxy paste on your concrete substrate. When you go a little bit to the FRCM for the grids, again, you have a unidirectional grid there and a bidirectional, just like what you would have for your typical FRP weave. So those would be the variations that you would get with respect to readily available products.
So I'm kind of jumping back, actually, since we already talked about strength, but something you just mentioned made me think about it. The epoxy that we're using, that obviously, like you said, has to transfer the force, from the member being reinforced to the fiber. Is that always going to be stronger? Is the epoxy that you have just so much stronger than the fiber or the carbon fiber that it's not what will fail?
Yeah, so you don't want a failure in your epoxy. You would always want a failure in your substrate. So if it's masonry or concrete, your bond has to be stronger than the substrate itself. So even when we are doing all the testing, what we are looking for is you need to pull some kind of concrete out when your FRP delaminates. Likewise, in a masonry structure, you want your part of your wall or the substrate to come out, and you just don't want a failure at the bond. So your epoxy bond is much stronger than the substrate itself. So that should be your failure mechanism when these products delaminate and fail.
Okay. On that kind of, we tend to think of structural products we use as really durable to the environment, especially concrete, right? Mm-hmm. Is fiberglass able to match, or FRP, the durability and especially the lifespan of a concrete structure?
Yeah, I mean, that's a good question. So the earliest fiberglass jackets that we've installed in the Bay on the East Coast were probably in the 80s, early 80s, and in the Chesapeake Bay Bridge, I think on the East Coast. So those fiberglass jackets are still existing right now. We have some jackets that were installed in northern Canada in icy waters that about 40 years ago that are still existing right now. So it has a long history of durability. Also, ICC ES AC-125, which has the testing methodology for these composite systems, also has durability testing. So it has to undergo a bunch of durability testing, freeze thaw, salt water, exposure to different elements. So we undergo those type of testings. I think they require 3,000 hour. Then Caltrans has 10,000 hour requirement. So it undergoes substantial amount of durability testing, just like your typical structural products would. So in addition to that, there are also reduction factors in the design. So if you're in an exterior environment, you have a reduction factor. Then if you are in an aggressive environment like a wastewater treatment plant or something, then you have a further reduction that you take from your material properties. So yeah, I mean, we take that into account when we are designing or testing products.
So we've kind of talked about using FRP to reinforce existing conditions. Are they always designed for, is currently the design methodology or the most of the use for existing conditions? And if so, do you see a future where it could be part of the concrete design in any sort of specific application?
So you're right. I mean, currently these products are mainly used in existing retrofit type structures. I mean, the benefit or the reason why it's used in existing structures is obviously it saves a lot of space. You're not adding a lot of weight to your structure. If you're trying to retrofit with typically adding more concrete or more steel, you're adding more mass. Typically in a seismic retrofit, your loads go up as you add more mass. So it has inherently has benefits in an existing structure type situation. In new structures, we use a lot of FRP for construction defects. So if you miss a rebar, you hit a rebar. I mean, we recently did a project where the column ties were not spaced correctly, so you can go back and correct it. Also, if your concrete strength is low as compared to what you designed for, you can go back and strengthen it with FRP. So those are pretty much the new construction type projects we've done. We are also looking at one project which came to us was like a houseboat. They were constructing new houseboats and they wanted to find a way to lighten the concrete element, the hull element of the lifeboat. So we designed it with like 6-inch concrete walls with some FRP strengthening on that, just to minimize the weight of concrete on the houseboat. So I see a future where it could be used more. I know FRP bars are now just got approved in using for new masonry construction. So the way things are changing, hopefully someday it will be used in some limited capacity in new construction as well.
So with potentially coming in reinforcing, in the construction phase, how does FRP reinforcing affect maybe the ductility requirements of, let's say, a special concrete shear wall?
Yeah, so FRP has shown to improve ductility in concrete shear wall type applications. In fact, we recently did some full-scale testing for concrete shear walls, and we did a control specimen. Then we just did with FRP on one face. Then we did with FRP and FRP anchors, and that's something that we've not spoken about, but these are FRP embedded anchors on the ends of the shear wall. And then we did more tests with FRP anchors along the length of the shear wall. And what we saw is that if you add anchors along the length of the shear wall, it actually adds 2 or 3 more load cycles at basically a higher cyclic load. So you get a lot more ductility in your shear wall. And conceptually, if you think of it like once your concrete starts cracking, right, in a seismic event, your concrete starts cracking. If you just strengthen it with FRP, your FRP kind of locally debonds. And then once your FRP debonds, it just keeps debonding along the length of the wall. So if you add anchors, then that anchors either prevent or reduce the debonding or delay the debonding at that location. And so your wall can basically take additional load cycles. So there are ways that you can anchor the FRP to improve or increase the ductility that you provide with strengthening of FRP.
I think I've seen these anchors in the catalog, but let me describe it. Tell me if this is the correct thing, where you're actually drilling into the concrete wall and putting in epoxy and fiber and then like filling that. It's sort of like a plug, and that weaves into the rest of the structure. Is that kind of right?
That's an accurate description. So we have two types of anchors. So one is where you put an epoxy and then you put the fibers and you splay the fibers on the fabric like you mentioned. The other one, we also have like a pre-cured anchor. So just where a part of the anchor that goes into the concrete is already factory saturated. And so it acts more like a threaded rod, right? So where you put an epoxy and then you just put the pre-cured part of the anchor into the concrete and then you splay the fibers again on top of your concrete. So that just kind of is easier to install because everyone's used to installing threaded rod type applications. So it's a similar type of installation.
Yeah.
But that's essentially what an FRP anchor is.
Okay.
So one thing I've heard before, and I'm curious on this, is that there may be some concerns with FRP when it comes to a fire condition, and how maybe it acts during a fire event. Could you elaborate, I guess, on that, or how what the testing has been?
Yeah, so the concerns are pretty genuine. So FRP, like I mentioned, is a combination of an epoxy and fibers, right? Every epoxy has a glass transition temperature above which the epoxy is going to soften and eventually melt, which is what is also true with FRP. So the glass transition temperature of most epoxies are around 160, 170 degree Fahrenheit. In case of a fire, the temperature will go above that and you'll potentially lose your FRP. So for gravity load upgrades, ACI has a check, which is called the existing capacity check. So you cannot design the FRP for the entire load. So your structure or member has to have a minimum load, support a minimum load combination. It's about 1.1 dead plus 0.75 live load. And then you can put FRP. So the idea is that if you lose your FRP in a fire or vandalism or anything like that, your structure would not have a collapse. I mean, it will still be able to withstand a minimum load combination. When you talk about seismic loads, that's not really the case because the chance of you having an earthquake and fire at the same time are not that high, like two extreme events. So in seismic conditions, we are less concerned about fire, but in gravity conditions, we do the existing capacity check just to make sure that even if we lose FRP, you're not compromised with respect to your structure.
Okay, that makes a lot of sense. Now, I guess on the other hand, when the FRP is on fire or going through a fire event, is it off-gassing some bad gases potentially with the epoxies? Just out of my curiosity.
No, I mean, it's funny you asked that question. I'm dealing with that question on two projects right now. So we have done ASTM E84 testing, which is basically the off-gassing testing, and we are in the lowest. So they have three different, I think it's Class A, Class B, Class C, and this falls under Class A, which is the least this thing. So it's not an issue with respect to off-gassing. It falls in the minimum, Class A, and I'm not an expert on that, but I think it's called Class A with respect to its lowest range.
Okay.
That you come with it. So we've done testing for ASTM E84 for that. So
if we're going to use an FRP product, are there any additional special inspections, or does any type of inspection go specifically with FRP products?
Yeah, so there is, and what I like to say when I'm giving a presentation is if your FRP is not installed correctly, it's just like an ugly-looking wallpaper, right? So it's you have to ensure that it's installed correctly. So the special inspections are required. There are some field tests that we do to check the bond between an installed FRP and the substrate. So it's just like a direct tension test. And you need a minimum 200 psi between FRP and the concrete substrate, or with masonry substrate, you just need either 200 psi or you need a failure in your masonry substrate. Also, we do some tensile testing. So they make these panels on the job site and send it to a third-party lab, testing lab, who do tensile tests on the coupons to ensure that the properties that they get match the properties that we publish on the data sheet. In addition, it's all, your surface prep has to be correct. Your surface has to be clean. Your temperature has to be within 40 to 90 degree Fahrenheit or 95-degree Fahrenheit. So all those things are just something that the special inspector would be observing on the job site.
Yeah. How variable can the results be in the final product if it's not installed perfectly versus, done exactly as it should be?
A lot. So if it's not installed correctly, I mean, we've seen projects where we have asked the entire FRP to be taken off the slab. I mean, this happened very recently on a project where it was just not installed correctly, and all the FRP had to be taken off and done it again. So you would FRP is something, if it's not installed correctly, you will see bubbles in the FRP, which indicates that it's not been installed correctly. You will see dry fiber if it's again not saturated correctly. So your results can vary significantly, which is why a good special inspection program is required for FRP.
So with your experience, you said you worked in the field for a few years. What are the most common questions you get from structural engineers? Maybe things that they're confused about when it comes to FRP.
So I guess the most common question I used to get from engineers who are absolutely not familiar with FRP is, FRP is, we've heard, is 10 times stronger than steel. It's like this magic, reinforcing member that can pretty much do anything that you want it to do. So, I mean, that is obviously not true. So, there are dry fiber properties and there are composite properties. And if you're looking at dry fiber properties, it's 10 times stronger than steel, but you never apply dry fiber on your substrate. So you need to be sure that you're looking at the right properties when you're designing things. The other question we get is, how much capacity can you really increase in a member? That again, answer varies. I mean, we can give ballparks in those type of situations, but it really varies on your type of substrate, type of application. And then, ductility is another big question that comes up, like, how is ductility addressed, or how, when you're doing a seismic retrofit type applications. So those are the most common, special inspections is something that comes quite often. So yeah, and then design related questions. If somebody is interested in knowing more, then obviously we go into the details of design and how it's designed.
With Simpson specifically, will they design the FRP solution for a project?
Yeah, so we have a design team that actually does all the FRP designs, and that is a no-cost service to engineering firms. So right from preliminary designs to sign and seal drawings, either before the before the permit phase or after the permit phase as a shop drawing, all those services are provided by Simpson. So if a project is going for permit, we do all sign and seal drawings and submit it to the engineer of record, who attach those drawings as part of their permit submittal. So that's quite, we do that quite a bit on, DSA or school or hospital type projects, where they typically don't want to approve a project till they see all the FRP calculations, because this is obviously an essential part of the retrofit, and it's not quite right to do it as a deferred submittal, I guess. So there should be something that is checked beforehand.
So then when we talked a bit about there with the engineers' confusion, what about contractors? What is that interaction like? What kind of questions do they have to Simpson when it comes to installing FRP?
So I think most of the contractors that we work with are quite savvy with FRP of what it can do and what it cannot do. So a lot of their questions are, if they see a design specified on the drawings, they are the best people to understand whether it's actually, if you can build it or if you cannot build it, or if there's some other way it can be designed. So a lot of our contractors give us input like, can we do it this particular way, or can we add less anchors with bigger diameter anchors and things like that, or can we add a thicker layer of FRP versus two thinner layers of FRP? Those are the type of questions that come up quite a bit with contractors. Also, on job sites, as you're aware, in an existing building, things are never the same as what your drawings show. So when you're on the job site, you're going to see something different, and you just have to come up with details to address site-specific conditions. So that's another area where we do a job walk with a contractor before the job starts to address any job-specific conditions or details that need to be addressed.
So, for the designer, Zach and I, as practicing engineers, what are the times where we should think as FRP as a good solution? What are is it, I've used it to strengthen a beam, I've used it to put a new opening in a concrete wall. Is it anything reinforcing concrete, like any condition, or, are there specific places it's better?
Yeah, I mean, if it's a seismic retrofit, a lot of conditions, I would say you could use FRP, like shear walls, diaphragms, slabs, collectors, column shear strengthening, column confinement. Obviously, you mentioned beams. What am I missing? A slab wall shear transfer is another area that you can use. So all these are really good applications for FRP. Obviously, they come with limitations. So, I mean, when you're adding FRP on a shear wall, for example, you're still governed by the 10 square root F prime C BD check. So you cannot, overly strengthen a wall by just putting more layers of FRP. There's this maximum to how much. I mean, you typically don't want to go more than 4 layers of thick FRP fabric. Otherwise, it's just too much FRP. So there's limits to what you can do, but within limits, I think a lot of cases with seismic strengthening is a good application for FRP. Even for gravity, if you pass the existing capacity check that I mentioned, again, FRP can do a lot for you with strengthening beams, columns, like vertical expansion. We did one building in Aspen area where they added 2 additional floors to an existing building where we strengthened the building with FRP. So those could be good applications for FRP. And we are talking concrete, but masonry, brick, clay brick, hollow clay tile, all those type of substrates also you can strengthen with composites as well.
All right.
So this next part we're going to kind of talk through the application, maybe concepts as well. So the first one, let's look at axial strength. How does FRP wrap of a column, let's say, increase the load capacity of the concrete column?
So if you're wrapping the concrete column, it basically the FRP prevents the concrete from dilating when the concrete goes under compression. So it's basically preventing the concrete from dilating and just crushing. So that's how it increases the axial capacity of the column. In essential, you can think of it like increasing the concrete strength. So several times engineers give us and higher F prime C, it's 4,000 psi concrete. We want it to be 5,500, and then you can wrap the concrete and get a higher concrete strength there. So that would be the principle of just preventing the concrete from dilating in case of compressive forces when the concrete goes in compression.
Okay, so it's just added confinement.
Added confinement, exactly.
Yeah.
You're just adding more confinement.
Okay, so I mean, in the case where it is confinement, like let's say we did have that column that you can only access 3 sides, are we still able to add compressive strength to the concrete by wrapping just around 3 sides?
Yeah, so we added on the 4th side, we did FRP anchors that kind of did not confine the bars completely, but we still added anchors through the column that gained some amount of confinement. The goal on that project was that these were shear control columns, and we wanted to change its behavior from shear to flexural failure, basically get ductility in the columns, and we wanted to increase the shear capacity of the columns. So by doing that, we were able to change the columns from shear governed columns to flexurally governed columns, and plus increase the flexural strength of the shear strength of these columns. And we basically shook the columns to a deformation of about 12 inches from the top. So you added quite a bit of ductility to these columns and added strength, as well as changed the failure mechanism of that. So Yeah, I mean, those were really good tests with some good solutions for three-side strengthening.
That's cool. And so, just so I can get my head around this, if we were strengthening a column, let's say we wanted both shear and axial added capacity, are we doing a wrap with the strands running? Oh, I don't know how you would say this, perpendicular to the column, and then another wrap vertical?
Yeah, for shear, it will be all perpendicular, so meaning horizontal, where you're just like your horizontal rebar for your columns. If you're increasing the flexural strength of the column, then you're adding vertical FRP oriented in a vertical direction, just like your longitudinal bars for your column. And then you'll potentially anchor it at the top and bottom, just like you would develop your steel in the foundation below or slab above.
Yeah. Something that we've already talked about, because FRP is often used to reinforce seismic systems. Can we expect to get up to the same level of performance that we'd have with a well-detailed seismic system, originally with a repair project?
That's a good question. So the answer probably would be yes and no, in the sense like uh, FRP is primarily used to strengthen an existing deficient structure to act as normal as possible, right? So I mean, you're adding a lot of strength, you're adding some amount of ductility, uh, and make it as close as possible to an original structure. Obviously, if you were to do it all over again, you would potentially put the steel and put that concrete, and it would be the best case scenario. Uh, but this is close to being normal, is the way I would put it. In some cases, you can add more strength than something that you have originally designed as well. So it's a case by case basis. There are some areas that obviously need more research, like beam column joints. One thing that comes in mind needs more testing, more research in that area. So in some applications, I would say yes. In some applications, I would say we need more work to be done.
Yeah, I'm curious. Knowing that Simpson does or is willing to do the calculations for the EOR, do you work with engineers that will do that themselves? And do you think as this becomes more commonplace, engineers will just be comfortable running these numbers by themselves, or is it very specific, to the product?
So I mean, in the best case scenario, I would like ideally the engineers to at least know everything, how it's done. And I always like to tell the engineers that, I mean, it's you guys' project. You guys are basically signing and sealing the drawings. You guys are the EOR. So it's, you need to know what's happening and how we are designing these systems. And at the end of the day, even if you don't want to design them, ask the right questions to the FRP designer, right? What are you providing with the design? What are the strains that you're taking? Sometimes just to kind of in a competitive bid environment, you could potentially see, people using higher strains or, using less anchorage to get that project or things like that. So I would really want the engineers to be more inquisitive and know the design, know the concepts. There are some engineering firms who actually do their own design, so we go and we educate the engineering firms. I've given like weekly classes to an engineering firm. We took shear of beams one day, and we just did like a 1 hour lecture for shear of beams, and then just teach them, and then they are to a point now where they do their own design. So a lot of engineering firms are kind of in the Bay Area, do their own designs, but then some don't, and we are always there to do the design. But we would like, best case scenario, we would like engineers to be asking questions when design it.
So with majority of the time connecting to an existing structure, is there any sort of testing of the substrate that needs to be done to make sure it is, let's say, sufficient to be to have FRP attached to?
Yeah, so ACI currently has a requirement of 2500 psi, suggested value of 2500 psi concrete. That's where most of the FRP testing has been done. So anytime that we see concrete less than 2500 psi, we like to go on the job site and do some testing to ensure that we have the 200 psi bond strength between your FRP substrate and FRP and the concrete substrate. So that's some testing that we go and do if your concrete strength is too low. That's something to look out for. For masonry, it's typically not a problem because your masonry always ends up being the weaker substrate. So you'll typically get a failure in your masonry when you're designing FRP on masonry structures.
Makes sense. All right. Well, we got one more question for you, but thank you so much for your time so far. But we'll get you out of here in time. Being involved in the FRP field, what do you see as sort of the future for FRP? Will things get stronger, or what direction is the development going?
So I see. I mean, it to be more and more mainstream as we go by. We are, just at Simpson, we are doing testing every single day with something with respect to FRP. I just mentioned about diaphragms, three-sided column strengthening. We just did testing on wood poles, splice testing with FRP. So we have a project here in California where, your wood poles are deteriorated and we are just splicing them with FRP. So we are going to test more and more applications with FRP. We just developed a new FRP part called shear transfer bracket to transfer forces from your existing concrete to new concrete. So instead of putting dowels and drilling long dowels, you can use FRP brackets like a truss-like element to do the shear transfer. So I would say, we are developing more things, testing more things. I'm sure other people are as well. So the field is increasing, and I'm with more and more, non-ductile building ordinances coming up in California, URM ordinances coming up. I see more and more use for FRP as we go forward.
That's exciting. Well, I hope to, I've used it a couple times. I hope to get more opportunities coming up here, and looking forward to just learning more about it.
Sure. You know where to reach us.